So we will begin the final presentation. It's from Stefan Sendlbeck. Hi. He comes from the Institute of Machine Elements of Technical University of Munich. His topic is a gear damage estimation and propagation approach by combining simulated and measured transmission error data. Let's welcome his presentation, Mr. Stefan Sendlbeck.
Gentlemen, a nice welcome to this year's International Conference on Advanced Vehicle Powertrains. We provide a gear damage estimation and propagation approach by combining simulated and measured transmission error data. The authors are Chief Patel, Dr. Michael Otto, Professor Carsten Stahl, and myself, Stefan Sendlbeck. We are all researchers at the Technical University of Munich in Germany. Based on the paper we published, the presentation contains a motivation in terms of gear condition monitoring. It contains the experiment and the measurement data that we used. We will provide and present the simulation concept with detailed steps of damage identification, virtual gear set generation, gear damage growth models, and the transmission error simulation. At the end, I will show you some results and application before concluding everything with a summary. Whenever we operate a gear system, it can lead to structural changes or any type of gear damage that consequently can lead to undesirable behavior or even to critical failure, what you do not want. So one possible way is to use condition monitoring so that you can implement condition-based maintenance strategies or operation strategies. If you want to do so, however, it is hard to retrieve high-quality run-to-failure data that is necessary because it is costly and often not available in large numbers. The result is that condition monitoring models lack the necessary precision for damage evaluation and prediction. So the question is, if simulated data is a solution, so can we extend our measured data with simulated data and retrieve better models? And the question here is if you can use the transmission error in combination with geometrical and temporal damage propagation models of multiple virtual gear sets to retrieve that. So what is our experiment and our measurement data? Our data is based on actual gear tests of an FCG back-to-back test grid. And after getting, for example, pitting or micro-pitting damage, we do before and after the tests flank measurements. So we tactilely measure our flanks, and then we calculate the deviation of our flanks of the involute profile. And that's what you can see in the image here. You see the tooth width, you see the tooth height, and the deviation at every point. What you can see in that image is, for example, marked with number 1, intended corrections, like a tip relief. You can see, as indicated with number 2, manufacturing deviations, or as indicated with number 3, pitting damage, micro-pitting damage, or any other type of gear flank damage, the one that we want to identify later on. So, how is our simulation concept that we provide with this paper? If you look at the left-hand side of that graph, measurement data, whenever we operate a gearbox, we can retrieve various signals, for example, the transmission error, the measured transmission error. If a damage occurs, we can do a damage evaluation, normally at the end and at the beginning of a test, and then we can correlate the measured transmission error to that type of damage. And of course, we miss everything in between, or it is costly to examine everything in between. So what we do now is we do tactile surface measurements at the beginning and at the end, and we use those measurements to simulate the transmission error of those flanks and to generate even more data. And how do we do that? We first of all do a damage identification in those measured actual from test retrieved data. Then we generate a multiple or many virtual gear sets. We do gear damage growth modeling as well in terms of time as well as in a geometrical sense, and then we do a transmission error simulation based on that, so we can extend our measured transmission error database with simulated transmission error, and we also have all the data between starting of the damage and the end, or the measured transmission error. And that's type of damage, or that type of data we can use for more precise damage evaluation, more precise damage prediction, and for flank surface reconstruction. So let's go through every step of that simulation concept. The first step is, whenever we measure a flank topography, we want to automatically identify the damage. The example you can see here is again the deviation from the involute profile, and in that topography you can see a micro-pitting damage, and you see our algorithm which automatically detects that type of damage in that topography measurement. How do we do that? We use a 4-algorithm unsupervised concept with algorithm thresholding. So we have 4 algorithms: Kenny edge detection, Otsu thresholding, a one-dimensional Fourier transform, and a one-dimensional Fourier transform with edge detection. And then we calculate the number of algorithms at each position that indicates a damage. And if the number exceeds a user-defined threshold, we mark that point as damage. And as you can see, for example, in red, if all 4 algorithms detect the damage at that position, it is marked as red in the picture you can see here. Of course, on the left-hand side, we see the tip relief, but as we know where the tip relief is, we can neglect that for further processing. The next step is, based on our measured topographies and the identified damage, we isolate the damage so that we only have the damage, and then we use that damage from multiple different tests and measured topographies to generate even more topographies. Of course, we always have to consider physical properties, which type of damage we combine, where damage can be and where it cannot be. But in the end, we can use a small data set of damage to retrieve a big data set of virtual topographies containing different types, different numbers, and different severities of damage. And then we can use those topographies to generate virtual gears, and with different number of teeth or different shapes. And then we can use those virtual gears to create virtual gear sets, so combining pinion and wheel for even more data. Of course, those topographies are still at the beginning and at the end of a test. So we want to simulate everything that is in between. And for that, we use our damage in the topography and simulate the damage growth, as well as from a geometrical point of view and a temporal point of view. So for geometrical growth, we use morphological image processing. We use structural elements like a cross or an ellipse, and we use image processing operations like dilation, closing, and opening. For temporal growth, we use characteristic information from experiments and from the literature, and what we retrieve is the damage propagation with respect to the number of load cycles. And if we combine all of that information, we can simulate or interpolate the damage between the beginning and the measured or the end of the damage, and then we can use that data to simulate signals. And that's what we do in the next step. So now we use our virtual gear sets and every time step in between to simulate the dynamic transmission error for every time step. And of course, as we do have a damage identification algorithm, we are able to map those signals to the degree of damage at that timestamp. And that's a way how we can retrieve continuous run-to-failure data for condition monitoring that extends existing measured data and also has more data than the actual measured one. Next, I will provide you some results when doing the image processing. So what we can see here is the morphological image processing, so the geometrical growth of the damage with 3 different types of structural elements or operation. So on the left-hand side, we see a dilation with an ellipse as a structural element of size 5 by 5. And the first step, number 1, is always known to us, as well as the last step, in that case number 9. So everything in between, not step 1 and step 9, is an interpolation. And now we can see that with our morphological image processing, we can retrieve 7 time steps in between. And if we, for example, use a different strategy, for example, closing with an ellipse, as you can see in the middle, the geometrical growth is a little bit different. And if we use, for example, a cross as a structural element, it's a little bit thinner compared to the other structural elements. So we can retrieve more time steps in between, because here, again, as with the other 2 examples on the right-hand side, the first and the last image are the ones that we know, and everything in between is simulated. And now we can use those images to add our temporal growth. So the time between each time step provided here is not linear, but we have to add our damage-specific growth model, and then we can use those images for our virtual gear set generation and then for our signal or transmission error signal simulation. So what is the summary of this concept? When we want to retrieve run-to-failure data for condition monitoring, that can be challenging, especially if you want to have continuous run-to-failure data of high quality. That's why we say, okay, we want to extend measured data, especially measured topography data, with simulated data using morphological image processing, using temporal damage growth models from the literature, and also using a dynamic transmission error simulation approach. So our approach, based on only a few measured data, can result in many simulated data, and it contains a damage identification algorithm, a virtual topography and gear set generation, a geometrical and temporal damage growth simulation or modeling, and at the end a transmission error simulation. With our approach, we can extend our database, and therefore it makes it possible to improve damage prediction, to improve damage evaluation, and even it enables to do flank surface reconstruction. Thank you. Dear ladies and gentlemen,
Thank you, Mr. Stefan Sendlbeck. So, is there a question?
Hello, Professor Sendlbeck. I have a question. Would you tell me how to get established the virtual gear set
So what we do is we have those tests that we do, and then we retrieve those measured topography data, and then we more or less use them as a mix. So the idea is to combine only few measurement data and generate multiple simulated ones. And how we do that is that we extract the damage from one test, and then we say, okay, let's generate a new one. And then we just say, okay, let's generate or create any type of gear. So we just choose the number of teeth freely, just what we want. We choose the shape freely, and then we add those topography data from another test to this newly generated gear. Of course, you always have to respect the physical properties, so you cannot just combine everything with everything, because that would violate how the damage occurs, how it happens. But apart from that, you're free to combine everything, and that's how we extend or how we increase, the database, or how we can generate those virtual gear sets. And then of course, you need a dynamic simulation tool where you can use those virtual gear sets for dynamic simulation.
So you mean that you get the virtual gear set from the experimental data, and your simulation, you use some software such as the MATLAB Simulink. Is that?
Exactly, that's exactly how we do it. So we use only few data from measurement, generate multiple virtual gear sets, and then we use a dynamic simulation tool. In our case, it's a dynamic force tool, or you can also use MATLAB Simulink for dynamic simulation, and that's how we retrieve the transmission error data.
Okay, thank you.
Thank you. Is there any question? Thank you, Mr. Stefan Sendlbeck. I have a question. I noticed you mentioned when you get the measured transmission error, you will build a damage growth model. So can you give some explanation about this model?
So as I explained, we have more or less the beginning at the end and the end of the damage we retrieve from measurements, and everything in between we want to simulate. And then we need two things. We need a geometrical growth. So on the flank, how does the damage actually increase or decrease? And the second thing we need is a temporal growth. So how does it change over time? When it comes to time, we use experiment data or data from literature. So we know, or we need to know how, for example, pitting evolves over time. That's one thing. And the other thing, in terms of geometrical growth, we use image processing. So it's more or less an interpolation, if you say it in a soft way, in a geometrical point of view. So we try to interpolate from no damage to the end of damage on a 2D surface. And that's where we use this image processing techniques of dilation, erosion. And of course, we need to validate in further steps which is the best way of doing this image processing interpolation. But once we have done that, it's a good way to simulate lots of data from existing measurement data.
Okay, thank you. Another question. Let me think. I noticed your research work. I think is a valuable reference for engineering. You mentioned the damage is macro pitting. So for this kind of damage, it requires the gear teeth topography. So what kind of the noise? Have you done some work about the noise using this method?
Sorry, I did not 100% get your question. Could you please repeat it?
I think your damage, you mentioned the micro pitting, the gear damage. So you got the gear profile topography. So you know the noise is another question for in the engineering. So have you done this kind of work to the gear monitoring about its noise?
Okay.
Yeah.
Okay, I think I got it. So what you're asking is that we have, or what we provide here is a micro-pitting example. I mean, this method doesn't only account for micro-pitting, but also pitting other types of flank surface damage. But the example here is micro-pitting. And yes, we have done tests where we retrieve the vibrational signal, or as you said, the acoustic emission, the noise, directly from a test rig. So we can compare the results of the simulation to the measurement or the measured signals as well, not only the transmission error, but the vibration signal as well.
Okay, thank you. So is there any question? So thank you again, Mr. Stefan Sendlbeck.
Thank you for having me.
Bye.